Now let us see the working of the PN junction biasing. Biasing in terms of electronics language is applying external DC voltage in order to achieve certain operating conditions. Depending upon the polarity of the applied voltage, this biasing is classified into forward biasing and reverse biasing. In forward biasing, you could see the positive terminal of the battery is connected to p-type material and negative terminal of the battery is connected to n-type material. As in the holes in the p-type material will get repelled towards the junction. Similarly, the electrons in the n-type material will get also repelled towards the junction. And as long as the applied voltage is less than the barrier potential, there will not be any conduction. But as soon as the applied voltage exceeds the barrier potential, this electrons will and the holes will start crossing the junction and the width of the depletion region gets reduced. Now the junction once when the applied voltage is further increased, the depletion layer disappears and now the junction offers a very low resistance, say this forward resistance to the current flow. Now the current flows in this low resistance path, and the magnitude of the current hereafter depends upon the magnitude of the forward voltage. And coming to the reverse biasing, in reverse biasing, the p-type material is connected to negative terminal of the battery and n-type material is connected to positive terminal of the battery. Here the majority carriers, that is holes in the p sides and electrons in the n side, gets attracted away from the junction. As a result, the width of the depletion region gets widened. Now the junction offers a very high resistance and there will not be any current flow in the junction, but practically speaking there will be current due to minority carriers in the order of microamperes, and this current is termed as reverse leakage current. So we can keep in mind that during forward biasing the diode conducts, and during the reverse biasing the diode does not conduct, it just simply blocks the applied voltage. Now coming to its VI characteristics, let me quickly get through this, take you through the VI characteristics, and you could see the total voltage drop across the junction, that is the forward voltage is equal to the barrier potential voltage plus IF into RF, where IF is the forward current and RF is the forward resistance. This RF is very small, we have already seen. And initially during the curve region OP, there will not be any current practically, because it is less than the cut-in voltage, and the region PQ, this is where the region your current starts to increase exponentially. That is, the point P is called the knee point or the cut-in point, the point at which the forward current starts to increase exponentially. From this forward characteristics, if you draw the slope for the change in voltage and change in current, you could get the forward resistance. So you could observe that the graph lies in this first quadrant, and the region PQ will be the operating point. And when you observe the reverse characteristics, the characteristics lies in the third quadrant. Initially, when you increase the reverse voltage, there will be an increase in the reverse current, but for a small duration only. It will soon attain saturation, and this current is called reverse saturation current. And when you further increase the reverse voltage, this current remains almost constant, but to a particular extent only. After a particular voltage called the reverse breakdown voltage, when you further increase the applied voltage, the junction breaks down and the reverse current increases enormously. Normally we will not operate the diode in this reverse breakdown region. Our reverse current is always limited to the reverse saturation current. From this characteristics, we can calculate the dynamic, we can calculate the reverse resistance, and as we told earlier, compared to the forward resistance, the reverse resistance is very large. And on analyzing the complete VA characteristics, we are going to analyze these characteristics under three conditions, that is with the zero external voltage and during forward bias and reverse bias. And you could see the resistance R in this. This resistance R is basically called the current limiting resistance. Previously in the forward characteristics we have seen after the new voltage the diode current increases exponentially with the applied voltage. So just to limit this forward current to the safe value, we are using the resistance R, and the diode current equation is I is equal to I naught e power V by N into Vt minus 1. During unbiased conditions, the voltage forward voltage V is equal to 0. As a result, e power 0 will contribute to 1. As a result, then I is equal to 0. That is, during unbiased conditions, there will not be any current. During forward bias, you could see from the expression, you could see I is equal to I naught into e power some term. Therefore, your this indicates your I is increasing exponentially. Under reverse bias conditions, you are going to change the V to minus V. As a result, I is equal to minus I naught, which means the current is in the reverse direction. Now let us discuss some very important terms. Breakdown voltage. It is the minimum reverse voltage with which the PN junction breaks down with sudden rise in reverse current. As I told you earlier, this reverse current should be kept under check because this reverse current, due to the flow of minority carriers, will also increase the junction temperature. And we have already seen this has negative coefficient of resistance. So when your temperature increases, your current will also increase. Once current increases, it will further increase in heat dissipation. As a result, it will end up damaging the junction. So this breakdown voltage should be kept under check. Then knee voltage, it is the minimum forward voltage at which the current through the junction starts to increase rapidly. That is the current at which the diode just begins to conduct. It is otherwise known as the turn on voltage of the diode, and it will be 0.7 in case of silicon, and it will be 0.3 in case of germanium. Also, you could see when the diode conducts, the voltage drop across the diode will be maintained as 0.7 in case of silicon, and it will be close to 0.3 in case of germanium diode. And here are the limitations in the operating conditions of PN junction. See, the operating of PN junction is limited to the following points. Maximum forward current. It is the high instantaneous forward current that a PN junction can conduct without damage to the junction. Normally, this maximum forward current will be mentioned in the datasheet provider, datasheet of the equipment manufacturer. You should limit this forward current, otherwise if excess current flows, your temperature will increase and eventually it will damage your PN junction. Next, peak inverse voltage. It is one of the very important parameter when it comes with working with rectifiers in choosing the diodes for rectifier operation. That is, it is the maximum reverse voltage the diode can withstand without creating damage to the junction. That is, it basically speaks about the reverse voltage blocking capability of the diode. Next, maximum power rating. Obviously, every diode will have its every device will have its maximum power rating, and maximum power rating means it is nothing but it is going to be the product of your voltage and current. So again, it is the maximum power that can be dissipated at the junction without damaging. This data will also come along with the data sheet. Now introducing the fundamental component PN junction diode. Nothing but your PN junction simply replaced with two external terminals available for external connections. Since it's a it is having two terminals, one is called anode and another is cathode. Two terminals, di plus electrodes, and it is equivalent to diode. And the P region is called anode and the N region is called as cathode. And similarly to the PN junction, the diode previously we have explained the terms with PN junction. You can simply replace the PN junction and insert the diode there. The first diagram shows the forward biasing and the next diagram shows the reverse biasing. Next, we are going to deal with the equivalent circuits, like how the diodes can be represented. In case of approximate model, you will be modeling the barrier potential as V0 and the forward resistance as RF, and you will have that ideal diode. So the total voltage will be equivalent to your barrier potential plus internal voltage drop, and this barrier voltage, as I told you earlier, it will be 0.7 for silicon diode and 0.3 for germanium diode. Here we are in this approximate model, actually we are linearizing the exponential portion. After that is, we have assumed that your diode current increases in a linear manner with the applied voltage after the cut-in voltage. Next, coming to the simplified model. In the case of simplified model, you are neglecting the forward resistance. There will not be any forward resistance, and as a result, the IF, there will not be any slope in IF. After a cut-in voltage, your diode will instantly start to conduct, and it will maintain the same voltage across it. Next, coming to the ideal model. Ideal model is nothing but ideal diode can be considered as a switch. The switch can be opened or closed. If the switch is opened, it is going to block the entire voltage, and if the switch is closed, it is going to conduct with zero voltage drop across it. And while analyzing the problems, it will be mentioned for us to use the ideal model or approximate model or simplified model. If nothing is mentioned, it is better to go with the approximate model.